Maybe we'll get started now. Okay, we are now recording. We'll go from the current slide and go from here. Okay. Is this podium in the way for anyone to see? This is where it was sitting. I haven't moved it. I don't need it, so if it's in the way, I'll be glad to move it. That thing was in the way, and that was a pain in the neck to move, but I got it moved. Okay. Any questions on anything we've done so far? Okay, we were going to go over safety first, and did we cover any of safety before? No. Okay. So let's hit it. There's 3 areas of safety we always need to keep in our minds so we'll know what to do if the emergency arises, and we don't have to wonder, hey, where do we go? What do we do? So let's think about it. What would be one of the 3 areas of safety we need to keep in mind? Fire, exactly. And this could also pertain to chemical spills or noxious fumes, things like that. What do we do? Let's get worst case scenario first, that it happens in this room. Let's say my computer blows up, and arcing and sparking and sets some of the papers on fire. What do we do? Say again?
Don't panic.
Don't panic. That's a great thing to not do. Okay? Don't panic. Yes. Any other ideas?
Pull the fire alarm.
Okay, yes, we need to pull the closest fire alarm. Does anyone know where that is? Okay? Right across the hallway here, there's a fire alarm box right there, right next to that exit that goes out there next to the office. Just within sight of the door here. There's the closest fire alarm. So somebody get out there and pull the fire alarm. Anything else? He's been in one of my classes before, so he should know. You're being tested here.
Fire extinguisher.
Okay, where's the closest fire extinguisher? Because it's happening in here, we do need to know about that. Where is the closest fire extinguisher? Okay. Right here, within a foot of where I'm standing, right here, closest fire extinguisher, just outside the door. Hang on. Can't get much closer than that. Okay? What else?
Call campus.
Aha, very good. The very best the call to make would be campus police.
On this campus, it might be better to call the 911 with the fire department.
Yeah, the fire department is so close. They will immediately get in touch with them too. But it's sort of political, our campus police doesn't want to be left out of it, and especially if they're over on that campus, doing tours, they want to get over here as soon as possible, and they will be calling. They are hardwired to the emergency responder. So if you have the campus police number, and make sure it's the Birmingham campus police number. Are any of you on the Lawson State app? I don't know if it's Cougar app, Lawson State app, whatever. They say at the very top of that, they have the numbers for each campus. Okay? If you don't have that, it's also found in other places. But if you don't have that on speed dial, 911 will do. Okay? So, those are ways we notify other people we've got an emergency here. So what do we do? Once we've notified everyone, we're out of here. Huh? Yeah. Okay, don't panic. Remember what she said, don't panic. But move out of the room and do it reasonably, calmly, not slow, but definitely not running. You don't want to hurt anybody else. And where's the closest exit? And you can't be in a much better position than we are here. There's an exit right there. There's an exit right there. In fact, 2 exits right here and 1 right there. It depends on, yes, it depends on where the smoke is coming from. If it's not from this room. If it's coming from this way, we go this way. If it's coming from that way, we go one of those 2 ways. Okay? So we've got 4 possibilities. to get out of the building quickly. Can I get your name, please?
Yes, Jennifer.
Jennifer, okay. All right. So we're talking about fire safety, okay? Now, is this part of the scenario? Hey, fire in the building. I know there's no more classes today. I'm out of here. No, okay? When you go out, now, I haven't seen a document for this building in particular. They have them. I put them on my wall and the other on the Birmingham campus. But in my mind, the safest place to be, the best place to go, would be out that door, and unless the fire is in that way, and go to the parking lot across the street there. That, to me, would be the best place to go. We'll be out of the way of emergency responders when they come. We don't want to be in their way here, and we want to get away from the building. So that's where we would go. Now, that's also, if we hear the alarm, that's where we proceed. Now, I'm the last one out of the room. If anyone's having difficulty, sprained ankle, twisted knee, something like that, I'm making sure you get out too. But I'm taking with me, unless it caught on fire, my roll book with a pen, and I'm going to call roll when we get out there in the parking lot there. So stay together as a group. If we can't account for you, someone's got to come back into a burning building, a chemical spill building, a noxious fume building, risking life and health trying to find you. That's why you don't take off and go. You stay together as a group. In a fairly short order, someone will be in touch with us and tell us what to do from now. More than likely this time of evening, it'll be go home. But you don't go home until you know that. Okay? So that's fire and chemical spill, that kind of stuff. There's one safety issue. Another one. Severe weather, excellent, okay? Now this will all come from outside. If we hear that alarm go off, now I've never been on this campus when they've done testing of alarms, because that's done, at noon on Wednesdays or 11 o'clock on Wednesdays or something like that. I've never been over here on that, but I'm pretty sure you can hear it pretty well, can't you? Has anyone been here? Okay. Pretty sure you can hear it pretty well, okay? I know in Bessemer you can. So if you hear that, and by the way, your hearing is better than mine. If I'm up here yakking away and don't seem to respond, say, hey, it's a weather emergency, okay? And if it is, what do we do? Say again? Don't panic, okay? Okay. What do we do? What is the general rule for weather emergencies? Okay, and where is a safe place? Okay. It's always interior. This is not safe. We're in a room with windows. Interior, lowest floor. Now we're on the lowest floor already. Safe there. Okay? Interior, actually, to me, in my mind, the hallway right out here is about as good as you can do. Okay? The advantage of it would be that the walls are rather close together. And I'm guessing, I'm pretty sure on this, I'm pretty sure that there is emergency lighting in the hallway. I can't see it for sure, but I believe it's with the exit sign. So that's the good place to be. Now, actually, not a bad place might be even the restrooms, because the walls are very close together. You've got a lot of corners. Trouble about the hallway is straight like this. A corner gives you more strength than a straight wall. But because the restrooms are on the outside wall, even though they don't have windows, it probably is safer to be in the hallway. And there's emergency lighting in the hallway, probably not in the restrooms. And you may not want to spend an hour or so in the restroom in the dark. Okay, so the hallway is probably the safe place to be. Again, you stay together. I'm the last one out of the room. We don't have to go far, just out into the hallway. We'll close the door in case there is a limb come flying into the room here. We don't last to be going out unless we close the door. and we hang together. I call roll, make sure we account for everyone. And then if you want to move around and visit with friends, as long as you stay in the safe place. So that's what we do for weather emergency. What's the third safety issue? Yes. Unfortunately, we have to think of active shooters now. 5 years ago, I don't think I would even cross my mind to bring up something like that. But today's environment happens. There has been at least one active shooter on a community college campus. That's the only one I know of. Many universities have had them, and then lots of other places, shopping malls, theaters, nightclubs, all sorts of places have had them. But I've only known of one community college, so it can happen. Okay.
So, last year, some guy called up here was threatening some people at the dorms.
Oh, really?
Yeah, so we were on lockdown in the dorms one night.
Okay. Was that? Did he have a weapon?
He just called.
Oh, called it.
and said
Okay.
he was-
Okay, well, I hadn't heard of that, but good to know. And so what do we do? Now, if it is actually an active shooter, again, I'm hard of hearing. You will hear it before I will. Let me know. Hey, that's a pop, pop, pop that sounds like gunfire. Okay, or rat-a-tat-tat. That's machine gun fire. What do we do? Okay. Here is the difficulty with that. Okay? This door does not lock from the inside. Okay? In fact, I don't have a key to lock it from the outside either. So all we can do is close the door, turn off the light. Now, if we hear the rat-tat-tat, okay, somebody call 911, okay, or campus police if you have that on speed dial. They need to know. As soon as that call is made, turn off the phone. We don't want phones ringing or any other noise in here, okay? So we close the door. We have no way of securing it. So what we'll do, and I'll do it, and if y'all want to help, you certainly can, is I'm going to put as many of these tables as I can in front of this door, okay, so that it makes the biggest blockage that we can think of to keep him out. Because he can open the door, but as long as the light's off and the door's closed and he doesn't hear anything, he may not stop by to check. But if he does, we want as many things in his way here as possible. Okay? Now, I haven't sized them yet, but I think if you stand that door on end, it goes past the top here. I believe it would. I don't know if that's good, bad, or indifferent, but I think I would put as many of them up like that as possible, and then get as far out here as we can, and then put some to block them, so when he does try to come in, he can't force his way in. Now, that might take some time. If we have the time, we'll do it. If not, the rest of you right over here. Now, the bad news with this is that is drywall, okay? Not concrete block like this. This is drywall, okay? But still, we get out of sight, okay? Now, if we have a bunch of tables set up here, then the tables, behind the tables, will be a pretty safe place too, okay? This active shooter thing, especially on this campus, in fact, I'm going to make a recommendation that every room have one of those toggle deadbolts from the inside. Every room ought to have that. So we can lock it. He can't get in. Okay? Now, yes?
Yes, I would suggest actually lining up against this wall because, they can see. If you have shooters or whatever, they can see inside, so they can see.
Yeah, okay, yeah. If the shooter is outside, we don't want to be visible there. And that it all depends. I was assuming the shooter in the building. Okay? If the shooter's outside, we hear it over there, then we're back in this corner. Okay? Or this corner over here. We're somewhere where we can't be seen. That's excellent. But if they are here in this building, and we blockade it as much as possible so they're in the building, we don't see anyone outside, then if I were you, I would start making my way out the window and try to get to safety. We're on the first floor. It shouldn't be too bad, and that would be my move. I will be the last one out, and guess what, guys? Okay, this doesn't. Not trying to make it sound heroic or anything. That's not my intent. But your life is ahead of you. Mine is pretty much back there. So if there is any confrontation, I'm going to make the confrontation, not you. And if I can buy you time, I will buy you time. And I will do as much damage to that truck as I can, and hold them off as long as possible. If any of you get involved with it, here's my suggestion to you. This sounds gross and everything. Go for the eyes. Okay? If I can control the weapon and stuff like that, someone literally claw his eyes out. If he can't see, he's pretty much incapacitated. Okay? So, but I don't want you doing that. I want you out of the room. Okay? Out of the building. And make your way to safety somewhere else. I'd say across the road into those double doors right down there would probably be pretty good. Okay? But otherwise, this is the worst situation of any of the classes I teach in, because the door opens out, no way to lock it, drywall walls, no place really to hide really well, so we just do the best we can. Don't sweat it. I don't think it's going to happen. Be thinking what to do in case it did. Okay? Don't lose sleep over it. Okay? Hopefully it won't happen. All right, any questions? Sorry we had to bring up those kind of things. So let's move on to where we left off last time. We're in Chapter 5, Forces, page 126. If you do have a book, top of the page there. Okay? We had just talked about force in 5.2, force and the law of acceleration. And this basically is Newton's second law. Okay? Now, and I meant to do one other thing. I really don't like teaching from the podium that much with my computer down here, because I'm going up and down, back and forth. Let me do one other thing I forgot to do. I had a student in my class last summer when I taught this. She insisted I do have a clean page to write on, because that slide that was coming up, the next slide is several pages over. So I'll come back to that when we need to get there. So let's go this one from current slide. Okay. Got it. Okay. Now, Newton's second law, the formula that best describes it is this. Let me get my pen activated. Goodness gracious. Okay, here we go. Force is equal to mass times acceleration. Now this is net force, not necessarily applied force. The net force acting on an object is going to produce an acceleration. If there's no net force, there's no acceleration. If there's no acceleration, the net force is zero. Gotta be. Okay? And the book doesn't put the N down there, but I do. A lot of places do. Now, what they're saying here, depending on the mass, but it doesn't really matter, the magnitude of the force is proportional to, now they use a little wiggly line. The more common one is like this. It sort of looks like a fish symbol. Kind of looks like an alpha in the Greek alphabet, but force is proportional to acceleration. The greater the net force, the more it's accelerating. The more it's accelerating, the greater the net force must be acting on it. Okay? Now, that was one observation that was made, and Isaac Newton and others did it. On the other hand, the mass is indirectly proportional to the acceleration, 1 over A. The greater the mass, the less the acceleration. The less mass, the greater the acceleration. I think I gave examples of this before. If I were to hit a golf ball with the same force that I hit a bowling ball, which is going to accelerate more? The golf ball, of course, because it's an inverse relationship. If the mass goes up, the acceleration goes down. The mass goes down, the acceleration goes up. That's an inverse relationship. All right. Now, what units do we have for these various entities? Does anyone know the unit for mass? Now we have two systems, SI system, which you can call the metric system, or we have US customary. What is the mass unit in the SI system? Kilogram, okay? If we said metric alone, you might say gram. SI is kilogram, because a gram is such a tiny amount of mass. If you think of an aspirin tablet, that's about a gram, okay? That's really small. This book is approximately, well, between 1 and 2 kilograms probably. So that's a more goodly size, okay? How about acceleration? Now, we talked about that, I think, last time briefly. What was acceleration? Anyone remember? Meters per second squared. It's the time rate of change of velocity. Velocity is meters per second, and the time rate of change of that would be meters per second, or meters per second squared. Now, what's the SI unit for, and that's the force unit, kilogram meter per second squared. That's given a name. Anyone know the name of that? That's named the Newton after Sir Isaac, and because it was named after someone, we use a capital letter. So that is a Newton. 1 kilogram meter per second squared. Okay? Now, I think we talked about this before. U.S. customary, we seldom, if ever, use a mass unit. But I did tell you what it was. Slug, okay, a slug. And then the standard mass unit for the acceleration unit for the SI and U.S. customary is feet per second squared. It's got to be distance per time per time. Distance per time would be speed, per time again would be acceleration, and this is how we define a pound, okay? That is what we know as a pound. Now, most of the time we just measure pounds. We don't ever measure mass in slugs. I don't know of a single scale that has slug as a unit in it. You just don't do it, okay? But that's what a pound is technically, okay? Now, they do talk in the book about a smaller unit of force. Now, the book is sort of anachronistic, sort of backwards. Really, they don't use this much more, but if you're dealing with small entities, what we call SI units, they used to call MKS, meters, kilograms, and seconds. Those are the basic three. For smaller units, they use the CGS, centimeters, about the width of your little fingernail, grams, which is about the size of an aspirin tablet, a mass of an aspirin tablet, and seconds. And in the CGS system, the unit for force is a dyne, D-Y-N-E. Now, I'm not even sure that has an abbreviation. I don't think it does. It's just you spell it out again. And a dyne, 1 dyne would be 1 gram centimeter per second squared. So you see just smaller units, okay? Very much smaller units. Don't worry about that. I don't think you ever have to use it. They just mentioned it in the book, so I said it. The SI unit is Newton, kilogram meter per second squared. The dyne is a CGS unit, which we really don't use much anymore at all. Okay, so let's do example 1. Can I erase these for now? Okay. What force, so we're looking for force, this is the unknown here. What force is necessary to produce an acceleration? Okay, so they give us an acceleration of 6.00 meters per second squared. Okay, now did we talk about digits last time? I don't recall that we did, okay? Let's talk about this. Now, why did they write 6.00 meters per second squared? Isn't that just 6? Second? Yeah, it's significant. In other words, this isn't just 6 meters per second squared. This is 6 meters per second squared to the nearest hundredth of a meter per second squared. This is a very precise measurement. Not just 6 or 6.0, 6.00, meaning this is precise to the nearest hundredth of a meter per second squared, which is a very precise. I don't know of many things that can measure accelerations that precisely. I'm sure there's equipment out there that can. You and I probably won't ever use one. Maybe you will. I probably won't. Okay? But that's what it means. So, our calculations, and we'll talk about this. Let's do a little bit more. On a mass, and here they give the mass of 5.00 kilograms. Okay? What is the force necessary to produce that acceleration on that mass? And again, that's not just 5 kilograms, that's 5 kilograms to the nearest hundredth of a kilogram. Okay? That means if you put it on a sensitive scale, it wouldn't read 4.95, it wouldn't be 5.03, it would be 5.00. Maybe if you had 3 digits out there, 001, 004, 4.9993, something like that. It rounds to 3 digits, 5.00. Okay? So what would be the force? All that yakking, the answer is pretty easy. Yes, the force would be, and you're right in the number, 30, but you need to give how many significant digits? No, 3. 3 significant digits here, 3 here, so it's 30.0. What unit? Newton. Very good. You could say kilogram meter per second squared if you want to write that much, or say that's a Newton. See, yes?
Okay, why did you say 30? Because I was thinking it was 2 also.
Okay. Exactly. Okay. In addition and subtraction, you keep up with the minimum number of decimal places. And there you can do. But with multiplication and division, what you're interested in is the number of significant digits. 3, your answer can't be more than 3. You count the number of significant digits. Any 0 at the end of a decimal number is significant. Okay? And we'll be seeing this in other ways. I'll try to point it out as we go. I won't give you all the rules now, but as we hit them, I'll tell you which zeros are significant and which are not. That 0 is significant because it's in between 3, which is significant, and the point 0 at the end of a number, that's significant, so any 0 in between is significant too. Okay? So that's 3 significant digits. That's what we round to. Guess what? 30 is an answer, okay? But to be precise in the book, it's 30.0. Okay? And the Newton is a kilogram meter per second squared. Let's move on to example 2. What force is necessary? So again, we're looking for a force. Is necessary to produce an acceleration of 2.00 feet per second squared. That is a good unit for acceleration, distance per time, on a mass of, get this, you'll never see it in real life, 3.00 slugs. Enjoy it now. You'll never see these in real life, I don't think, at all. So what's going to be the force? .00, what unit? Pounds. Okay, that's the SI unit for force in the metric, in the U.S. customary system. Now, I don't know if you realize that. Weight is a force. So pounds is a perfectly legitimate. If you were to weigh yourself on a metric scale, the weight would be in newtons. But most of the time, the scales in the grocery store are not measuring newtons. They're scaled for kilograms. That's a mass unit, not a weight unit. We'll get into that a little bit later. But, excuse me. Y'all awake yet? Okay, good. Have to do that every now and then just to make sure. All right, now we'll turn the problem around some and do it this way. find the acceleration, so this time acceleration is the unknown, produced by force, and this will be a net force of 500 newtons. Now, when the book writes it with a line over that, that means that zero is significant, okay? If they had no lines over it, that would be one significant digit. That's not after a decimal number, that's at the front. So without the line there, that would be one significant digit, 5. If they put it over the middle zero, that would be two significant digits. Over the second zero, 3 significant digits. So that's what that line means, okay? Bar, whatever you want to call it. If you had a mass of, applied to a mass of 20.0 kilograms. That's pretty massive, by the way, okay? Now, that zero, the third third digit is significant because it's after the decimal point at the end of a decimal number, okay? So that's significant. You don't have to put a bar there. So how do we get acceleration? Now, let me give you 2 ways to do this. One way is what I call sort of analytically, and if we know the formula is force is equal to mass times acceleration, if we're looking for acceleration, we divide both sides by mass. And that gives you acceleration is equal to force over mass. Okay, and you can do that. If you want a nice, easy little way to do it, now I first saw this when I was in the Navy and went to Navy schools. I understood doing it this way. That made sense to me. But I saw in the Navy they use this as a sort of a help. It's either the triangle or the circle method. Now this only works when you have formulas like this, F equal ma. One side is equal to a product of the other side. 3 variables, and they're related to each other in multiplication or division. Okay? And here's how they did it. Now you can either use the triangle method or you can use the circle method. It's the same thing, it's just whichever shape you like better. Okay? All right? The horizontal line is a dividing line. You know that. 7 divided by 3, you could put 7 over 3. That's the dividing. The vertical line is a multiplication line. So if you have a formula you know, the thing that stands alone you put at the top. Force. Force. And then the things that are multiplied put on either side of the multiplication line. Mass times acceleration. Mass times acceleration. So you have to know your formula and where they go. Now, if you're looking for acceleration, which in this problem we are, there it is, the acceleration is the unknown, what you do is cover the acceleration, and then what do you have? Force divided by mass. Force divided by mass. And that works for all these. And we're going to run into bunches of problems that do this. In fact, we already did. I just didn't show it to you. I don't think I showed it to you, did I? Okay. When we said velocity is equal to distance over time. That works. Distance goes on top. Velocity times time goes on bottom. Distance over time equal velocity. Okay? You see it works for all. Acceleration, velocity divided by time. Velocity on top divided by time gives you acceleration. Okay? There's lots of them. When we get into electricity, Ohm's law, power formula, just all over the place. And when we get next chapter, when we do work, work is force times the displacement. There we have it. Work up here, force times displacement down here. Anything that has that kind of relationship, one is equal to a product of the other. One is equal to a quotient of the other. You can put them on that. Whatever's on top in the quotient goes on top here. When one is equal to a product, the main thing goes on top, the product goes on the bottom. Okay? So, either way you do it, the acceleration is force over mass. So what's your force? From the problem here. 500 newtons. Now, when I'm doing the division, I like to put the fundamental units down there. Okay, what is a newton? It's a kilogram meter per second squared. Now, I'll show you why I like to use those units. Divided by the mass, 20.0 kilograms. I hope you see. Notice the kilograms cancel out. If you had newtons in the top, it's not obvious that anything cancels. When you put the fundamental units there, it's pretty obvious they cancel. Now, to do the math here, you can pull out your calculator and use a calculator, or if you want to do it by hand, this 0.0 here is only there for significant digits. You can divide both numerator and denominator by 10, and you have 50 divided by 2, and what would that be? 25, but then you put in the 0.0 because you need 3 significant digits, and that would be meters per second squared. Let me tell you something, folks. That is an enormous acceleration. That means it's increasing its speed 25 meters per second every second. In just a few seconds, you are going to be going so fast, you're going to break the speed of sound. Okay, or maybe the speed of light. Yeah, okay. So that's an enormous acceleration. Most of the time, you will not see accelerations that big. This is sort of a made-up problem, so you got it. Okay? Any questions on that? See how it works? You don't have to do the division in your head. You can use calculators. They'll give you the right answer if you plug them in right. So at the end of 5.2, there are some problems here. And if I'm not mistaken, in the back of the book, chapter 5, let me find it to make sure, 5.2, your odd number answers are in the back, so therefore I suggest you do the odd number problem. Now, you don't have to do them all. There's a whole bunch of them there, but I would do samplings of all that until you feel good, warm, and fuzzy that you have this mastered. Okay? Do some that are looking for forces. Do some that's looking for accelerations. Do some that are looking for masses. Do some that may be using SI units. Some that may be using U.S. customary units. Okay? Do a few of those. You don't have to do all of them, but do quite a few. And do any of the odds 1 through 33. All right. Good deal. Now, I already alluded to what comes next. Anyone needs what I have on the screen any longer? Okay, let me erase that. And if I hadn't told you before, the book is pretty good. The PowerPoints stink, okay? They hardly have any PowerPoint, just one here, one there, several pages away. The test bank, the questions aren't bad. Well, actually, some of the questions are. The first chapter, they're going to be fine. Later chapters, they leave out information, and I have to give them to you. But the keys are rotten. I have to check this by every answer because half of their answers are wrong. I'll say, that doesn't seem right. I'll check it, and yeah, it's wrong. So anyway, that's why I'm having to use this. Okay, but it's recording everything I say, everything that's projected, even the stuff I write. It's not projecting my arm waving. You can't see that. All right, now we're going to look at gravity and weight. I've already hinted at this when I said, notice the unit for force in the U.S. customary unit system was pounds, and that's what we usually use weight. Weight is a force. So this is talking about gravity and weight. The weight of an object is the amount of the gravitational pull of whatever gravitational field you happen to be in. And guess what? Has anyone ever been other than on the surface of the earth? No one in this room, okay? A few people have been to outer space and been, maybe a handful have been on the moon, but most people haven't been at those places. So our whole lives we spend on the surface of the earth. And the gravitational acceleration on the surface of the earth is constant just about everywhere. So we've never experienced any gravitational pull except that of the earth. Okay? Gravitational pull is a force. Pull is a force. Okay, remember? So a weight is a force. Okay? Now, it's not a net force. It's one of the forces that are acting on an object. It may, in some circumstances, be a net force, but the formula goes the same way. Now, this book uses a slightly different setup, and it's fine. They use weight as F sub W. Okay? That's not net force, that's the force due to weight. Okay? Well, a force is a mass times an acceleration. Well, the acceleration due to weight is the acceleration due to gravity. So we call that one G. Okay? Now, everywhere on the surface of the Earth, the acceleration due to gravity in the SI units is 9.80 meters per second squared. That's an acceleration due to the force of gravity everywhere on the surface of the Earth. In the U.S. customary system, that is 32.2 feet per second squared. Has to be an acceleration unit, and that would be it in the U.S. customary. Now, most of the time, when you're doing these things by just estimating, they'll say 32. But to 3 digits is 32.2. A lot of books will just use 9.8. That's just the 2 digits. To 3 digits is 9.80. Same number, but the extra digit out there. Okay? The F sub W means weight. In many other books, they actually use the symbol little w for weight. This book uses F sub W, emphasizing it as a force. Mass is still mass, same as before. Okay? So, all right, to erase this so I can do a problem. Anyone need that any longer? Okay. So here's example 1 in 5.3. Find the weight of 5.00 kilograms. We're looking for weight, which is F sub W. This is what we're looking for. And they give us 5.00 kilograms. What in the world does that measure? What does kilogram measure? I thought that was a weight. When I bought those beans the other week, they had 5.00 kilograms on the package. I didn't know what it meant. I looked and saw how many pounds it was. But kilogram does not measure weight. It measures mass. Okay? So this is a mass measurement. So what is your force? Force due to... What is the weight, which is F sub W? Formula I just had up there. Mass times the acceleration due to gravity. That is still an acceleration because mass times acceleration produces a force, and that will be your weight if that's the acceleration due to gravity. So since we're in kg, what kind of unit is that? SI unit. So therefore, what G will we use? So F sub W is equal to 5.00 kilograms times 9.80 meters per second squared. That's the acceleration due to gravity. That is G in the SI unit. And you might need a calculator, but you probably don't. That, I think, comes out 49.0. You got to have 3 digits there. What units? Newton, exactly. A kilogram meter per second squared is a Newton. Just like it is in a force, it is in a weight. So when you're buying so much many beans and you want the weight of beans, you're buying newtons of beans, not kilograms. But in the grocery store, everything's listed as pounds or ounces and grams or kilograms. But they're different things. They're totally different things. Those are masses. These are weights. Okay? Why can they get away with that? Because the acceleration due to gravity is a constant anywhere on the surface of the earth. And I'm not going to eat those beans anywhere but on the surface of the earth. So you're okay. You're okay with doing that. It's not correct, it's not precise, but it is okay. Okay? So 49.0 newtons. You'll never see this anywhere else except maybe this book. Find the weight. So again, that's F sub W. That's what we're looking for, of 12.0 slugs. Ooh, those little slimy things that are on the ground? No, that's not what they're talking about. What is that a unit of? That's also a mass. Okay? So what's the formula for weight in the U.S. customary unit? Same as it was before, mg. But now the m is measured in slugs, which is 12.0 slugs. I'm not even used to writing that, okay? And what's g in the U.S. customary? 32.2 feet per second squared. That's the SI unit for acceleration. I mean the U.S. customary unit for acceleration. That one's going to need a calculator, folks. I'm not going to do that one in my head. So if someone has a calculator, and by the way, when you're doing your test, when you're doing your homework, please have a calculator. Don't be, I mean, it gets so frustrating having to do all that by hand. Someone punch that in. Now, notice in the South, we're pretty violent. We punch it in. Other parts of the country, believe it or not, they press it in. They press the buttons, you know. We punch them, or we mash them, okay? We're pretty violent down here, aren't we? Actually, really, when I was living in Nebraska, I did some graduate school in Nebraska, and I had a friend who was from North Carolina, and she got ragged all the time from mashing buttons or punching buttons, you know. No, we press the button. You know, we're not that violent, you know. So what do you get? 12 times 32.2. Say again? 386.4. What unit? Huh? There's going to be a unit. Pounds, exactly. Now, what's wrong with the picture? It's a correct number, but what's wrong with it? 4 digits of precision when you only had 3 coming in. You can't get more digits of precision coming out than in. So what do we do with a problem like this? You only have 3 significant digits, so count 3 digits. 1, 2, 3. Look to the right. That number is less than 5. We throw it away. So it's 386 pounds. Okay? 386 pounds. Why, what?
What it means significant digit.
Okay, when you're multiplying or dividing, you can't get any more precise answer than you got coming in. So if this had been just 12 slugs without a 0.0 there, that would have been 2 significant digits. 32.2, 3 significant digits. The answer then would have been 390 pounds because you can't get more precision out than what you put in. And you only had 2 digits going in, you only can get 2 digits coming out. Count 2 digits, look to the right. The 6 would have been greater than 5, 5 or more, so you round up the one on the left. Yes?
So you take the lowest number of significant digits?
Yes, you take the lowest number of significant digits when you're multiplying or dividing. Exactly. Yeah, very good. And look, that's just... I'm not saying it's not important, but it's sort of minor. The answer is the more important. So on your test, when you give me more digits, I'll just cross them out. If you don't give me enough, I'll put them in. I don't take off points for it. If you got wrong digits, you lose points. Okay? Okay. But, all right. So that was example 2. All right. Now we're ready for finally, the next PowerPoint slide. Okay? Oh, that's not what I wanted. That's what I want. Okay, that one. We'll go from current slide. Now, This is talking about something that we really aren't going to mess with too much, but it's an important thing to know. Remember I said most of the time your weight is not your net force. Most of the time it's not producing acceleration. The time it would be is when you jump out of an airplane, which I'm never going to do, knock on wood. Okay? If I can help it, I'm never going to jump out of an airplane. Okay? Some of you maybe, that would be thrilling to you. For me, that would be Vomit City. You know, I don't want to go there. Okay? But then, if that's the only force acting on you, that's your net force. I don't want to be in that position, falling without anything else. Now here is a block, maybe it's a brick, it looks red like a brick, sitting on a table. What's the net force on that brick? Net force. Is it accelerating? No. So the net force has to be zero. Now I know the brick has mass, and there's acceleration due to gravity. We assume this table's on the surface of the earth, so it has an acceleration. That brick has weight. If you picked it up, yeah, it has weight. So there is a weight pulling downward, always toward the center of the earth. That's where the acceleration of gravity is pulling toward the center of the earth. So something must be pushing up on the brick to have zero net force. And that would be the normal force of the table on the brick. Okay? And that's what we mean by normal force. Normal means perpendicular. Okay? Orthogonal. Right angles. That's what normal means. That is the force of the table pushing up on the brick. And that's why I said most of the time the weight is not going to be a net force, it's going to be a component force. One of the many forces acting on the brick. Okay? Did I give you, when we were talking about net forces and things like this, I may not have done this. Did I talk about a jet plane flying at 500 miles per hour? Did I talk about that? Okay, let's do that example now. Let's imagine we have a jet plane. Oh, it might weigh several tons, okay? Jet plane weighing several tons, flying at 500 miles per hour, constant speed, level flight. What's the net force on that plane? Huh? Say again? No, I said the net force acting on it.
So I wanted to make sure.
Yeah. Net force acting on the plane. Traveling a level flight, 500 miles per hour, constant speed, not turning, straight line. What's the net force acting on it? The question to ask yourself from Newton's second law, is it accelerating? Is it changing speed? No. Is it changing direction? No. So it's not changing its velocity? No. Zero net force. Okay, zero net force. Now your question was quite good. You know that gravity is pulling that plane downward, don't you? That something has to be pulling up if it's flying at a level speed. And that something that's pulling it up is something called Bernoulli's force. I didn't show you this, did I?
You did with the paper.
Did I? Okay. And the reason? When you blow across, an increased velocity on top gives you a change of pressure, and that change of pressure is what gives the airplane lift. That's why airplane wings are shaped like this. Bird's wings are shaped like this. The air going over the top has to go faster than the air on the bottom, and therefore you get lift. That's why the planes have to get up a really good head of speed. That's why the runways are so long, and finally they lift, because you get enough difference across the wing in speed, airspeed, that it lifts you off the ground. So that's what's providing the lift. So gravity is pulling down, Bernoulli's force is pulling you up. The engines are pushing you forward, air resistance is pushing against you, but the net force is zero. Okay? Net force is zero. Same thing here. If that brick is not accelerating, which it doesn't look like it is to me, I don't see it flying off the table, I don't see it crashing through the table. It's just sitting there. Net force is zero, therefore the weight of the brick, which I know is a weight, it's heavy, is pulling down by the acceleration due to gravity. The tabletop is pushing up with a normal force exactly equal to the weight. Therefore the net force is zero. Okay? That's called the normal force. Okay? We're not going to do much more with it than that picture, but we did do the picture. Now, as I said, all of us live on the surface of the earth, right? We spend all of our time on the surface of the earth. Even if you were to climb Mount Everest, which I'm never going to do, the acceleration due to gravity is still very close to 9.80 meters per second square, or 32.2 feet per second square. Even if you're down at the bottom of the Dead Sea Valley, which is the lowest point on Earth, your acceleration due to gravity is still very close to 9.80 meters per second square, 32.2 feet per second square. It doesn't change appreciably anywhere on the surface of the Earth. Okay? However, those few people who have escaped the Earth's atmosphere and gotten out of at least some of the pull of gravity and gone into a spaceship, what do we say they are? They say they're weightless. They're really not. They still have a little bit of weight. It's just not very much. But you've seen them float around in those capsules, haven't you? Everything floats around in a capsule that's not nailed down, basically. In fact, when space travel came up, that's where we came up with Velcro, because they had to have something to keep things from floating around, so they put Velcro on it so they could stick to the wall and things like this. Otherwise, everything would have been floating around. So there's an advantage of the space program that we use every day.
The mass does not change.
The mass doesn't change. Excellent. The weight changes because the weight is a variant. It depends on the gravitational field in which you're located. But the mass is still the mass. It's an invariant. Your mass doesn't change. So that's why that 5 kilograms of pears is not the same as so many pounds of pears. This is measuring mass. That would be the same mass of pears if it was on the moon. That would be a much lighter weight of pears if it was on the moon, because the moon's gravitational field is much lighter, less than that on the Earth. So that's why it really isn't fair to say. But on the surface of the Earth, they just differ by a constant. And so we can refer to them that way. Not right, but we can. Okay? So, we're going to do a problem using that. This is example 3. And I hate to go back to this, but let's do it. Okay. Got to find the right slide. There it is. Current slide. Get my pen color back. Okay. Example 3, page 130. Find the 75 kilogram astronaut's weight on the moon. So what does the 75.0 kilogram, what does that represent? Mass. That's a mass unit. And we're looking for the weight. What is F sub W? Okay. On the moon, where G for the moon, I wish they put that on there, G for the moon is 1.63 meters per second squared. What would be his weight or her weight there? 75 kilograms, that's probably a he. I don't know. Okay. How would you get that? What's your formula? Weight equal mg. Weight is always mg. What's the mass? 75.0 kilograms, SI unit. And G for the moon is 1.63 meters per second squared. Another calculator one. Pull out your calculator, see what you get. And most calculators on phones will work pretty well too. What you get? Second? One what? 123. That sounds like a good answer to me. What unit? Second? Newtons, exactly. Now, did you round properly? Now, they said not. What did you get? Tell me the digits you actually see on your calculator. 75 times 1.63. Okay, say that a little louder. 122.5? 0.25. So they did it wrong. If you did your math right, they did it wrong. Okay? No, 25. Count off 3 digits, look to the right. That 2 is less than 5, so you throw it away, so it's 122 newtons. So they did it right. 122 newtons. All right, 122 newtons. Okay. Count off the number of significant digits. That's 3 and 3, so it's going to be 3, 1, 2, 2. Look to the right. That was a 2, 5 you said. That 2 is less than 5. Toss it. All right, then they have a little blurb here on mass versus volume. Now, I don't know why you would be confusing mass and volume, but let me just give you a few of the units for volume. Technically, SI unit would be cubic meters. Meter times meter times meter. For instance, let's say we wanted to know the volume of this room. What you would do, you would measure the length of the room, you measure the width of the room. Now you have to account for that little thing there, and you measure the height of the room. If that was in meters times meters, that would be meters squared. We talked about the floor having so many square feet, square meters of thing. If you're measuring tile, that's what you do. Flooring, going to what is it? Something liquidators. Whatever. Second. Yeah, lumber liquidators. Yeah, if you're going there, you tell them how many square feet or square yards or square meters you have the floor to cover, and they tell you how many bundles you need. Okay? But if you're wanting the volume of the room, it's length times width times height. Meters times meters times meters is cubic meters. Or feet times feet times feet is cubic feet. Yards times yards times yards is cubic yards. Inches times inches by inches is cubic inches. Centimeters by centimeter by centimeter is cubic centimeters. And y'all run into that. Some of you are nurses, right? Or not? No? Oh, okay. Last class, most of them were nurses or in some sort of nursing field. Okay. So those are volume measurements. However, there are a few others that are volume measurement that don't have the cubic unit by it. Okay? And I would like to borrow one of your containers if it has a thing on it. Okay? Okay? Nope. Yeah, whoops. Yeah, I guess it doesn't. It doesn't say what the capacity of this is. It's what? Oh, there it is, there it is, there it is. 30.4 fluid ounces. That doesn't have any cubic measure in it. Or 1 pint and 14.4 fluid ounces. Or 900 milliliters. Those are capacity measurements. And they relate to cubic feet, cubic inches, cubic meters, or things like this, but they're not the same. Okay, well, they are. They're usually in liters, quarts, gallons, fluid ounces, milliliters. You know, those are the type of things we see. Now, a lot of time in medical situations, you'll be running into milliliters. In the old days, they were cubic centimeters. But guess what? A cubic centimeter is the same as a milliliter. My mom was a nurse, and she used to talk about so many cc's, cubic centimeters. Have you heard that? Yeah. Okay. Nowadays they talk in milliliters. Same number, it's just the different units. Okay. They're exactly the same size. Okay. In fact, this is a sort of a dumb question, a dumb illustration of that. When you're talking about cars and car engines and stuff like this, how do when the people really find out about the cars, what they refer to? This is 323 or 1.4 liters. Yeah, okay. They talk about cubic inches, liters, and stuff. What do they talk about? Displacement of the cylinders. The more displacement you have, the more usually power you have, right, in that engine. Now, one of the car companies, popular car company today, started out as a motorcycle manufacturer. Maybe more than one, but at least one did. Okay? And what they did when they started building cars, they just took their biggest, most powerful motorcycle engine and put it into a car and built a car around it, you know. And that early car was, let's see if I can remember, 105, and they were a metric type country, not U.S., 105 cubic centimeters. Okay? 105 cubic centimeters. And they named their car after that. No, it was 104. I'm sorry, 104 cubic centimeters. Okay? Sorry, I forgot that. 104 cubic centimeters. Because, and what they did, clever them, and they weren't from Rome either, but they used Roman numerals. 100 is a C, and 4 is IV, and then they use CCs. Guess what they named that car? A what? Civic. It was a Honda Civic. Honda used to only make motorcycles. Then they started building cars, and one of the first ones they built was the 104 cubic centimeter, which is a really small engine, okay? And that was their Civic. And that's where they got its name. Or at least I've heard this. I don't know for certain if that's true. That's where they named it a Civic. Okay? If you ever wonder why they got the name Civic, I think that's where it came from. But that's neither here nor there. So I don't think you're going to confuse mass and volume, but it had a little blurb in the book, so we did it. That finishes 5.3. So homework exercises here. I would do either 1 or 3. And I probably should have said this on the last one, too. I didn't think about it. Yeah, on 5.2, I would do some of the odds 1 through 7, some of the odds 9 through 15, and then some of the odds 17 to 33. Now that I see they split them up into groups. So on 5.3, on 131, I would do either 1 or 3 or both. And then do either some of the odds 5 through 9, and then do some of the other odds. Well, I would do 11, and then either 13 or 15, just looking at what they're asking for. Maybe 17. So, you know, just pick them out like that. They're asking for different things, so you'll know how to do the different type problems. And the answers are in the back of the book for the odd number exercises. Okay. Now, remember my illustration of the plane flying, okay? And I said the engines were pushing it forward, but air was pushing it against it. And you know the faster you go, the more air resistance you have, right? I can remember as a kid, now I shouldn't have been doing this, but it just was so neat to do. I like to stick my arm out the window, okay? We didn't have air conditioning in our cars when we were in the South. We grew up in Georgia, so it was hot. So we always had the windows down. I like to stick my arm out. Now, when we're going along at a slow speed, you can feel the resistance there. But going along at a pretty high speed, my father never drove much over 55. But still, that would yank my arm back there. I could have, but I just liked doing it. I was weird. Okay, still am. Okay. So anyway. The greater the speed, the more air resistance. What is that doing? What is happening? What is it when I was trying to push this car over? Those who were seeing it early, that was a hard thing to do. Why? Friction between one of the wheels isn't turning and it's all canted and stuff. It was hard to move. Okay, friction. That's what air is. Air has friction. Water has friction. Okay, I pull on the table. Ugh. You can hear it hitting the floor. That friction. Pushing back. You can see it bounce along because of friction. Okay? That's why, now if that were ice, pure ice, and this wasn't, I could do that and it just slide really easily because there's very little friction with ice. That's why on an icy road, you better slow down because your tires are not going to hold. They're not going to stop. They're not going to hit that curve. You turn the wheels, you just keep going straight because there's no friction there. Okay? So friction can be a good or a bad thing. That 5.4 is going to talk about friction. Yes? Second?
You said there's no friction or little friction?
Very little. Very seldom do you have no friction at all. About the closest you come to that is outer space where there's no air molecules at all. Then you can almost say no friction. Ice, because an ice skater can change direction, there's got to be some friction, okay? But it's minimal. It's very little. But if it's pure slick ice, it's very little. It's very close to zero. So friction is a force that resists the relative motion of two objects in contact caused by irregularities of the surfaces. Okay? Let's see. I can't remember what my next slide is. I hate going back and forth between these two because it's such a pain. No, that's not what I want. I want this. Okay. Discard this. Go back to this. Let's see what the next slide. There it is. I thought that slide might be on here. All right, so we'll go here from current slide. Now, here's what they call a front end loader or something like that. A pretty powerful machine. If it's trying to push this block along, why do you need that big heavy machine to push that block along? Well, because even though it looks like this may be a sort of a flat level surface, and it looks like that may be a flat bottom, they really aren't. That probably is a gravel type road which has a lot of irregularities in that surface. And the bottom of this probably isn't perfectly smooth. It has irregularities. And when this irregularity here gets down into here and you're pushing this way, it's not wanting to move. You have to push it up the thing. You see, this shows that it's almost on the top, so it's going to go pretty easily. But if this were down in the hole and that was down in a hole and you try to push them, you're pushing against something. That's a lot of friction. So the rougher the surface, usually the more friction you have. And all surfaces have some microscopic amount of roughness to them. Even ice most of the time. If it's perfectly slick ice, very, very little. Okay? So, if your motion is this way, you're pushing on that way, friction always opposes the motion. You can bank on it. If you're trying to pull it this way, friction's pushing that way. It's always opposing the motion. If you stick your hand out the window, you're going this way, the air resistance is going to push you back. Okay? Always resist the motion. It's just contrary, isn't it? Friction is just a contrary force. Okay? Now, same thing here, that's magnified. If your motion's this way, the friction's that way. Guaranteed. Okay, let's see if this next slide is on. Yeah! Here are a few of the characteristics of friction. Do most of you have books, but some of you don't, right? Let me write these down because they are pretty... Okay, well, first, there's two types of friction. Well, actually, you might say there's more than that. We're going to talk about two types. The first we have is what we call static friction. That means stationary, not moving. The second is called kinetic friction. And kinesiology means motion, if it's moving. Now, I'll give you the example. You almost saw the example of this earlier. Okay? I'm pulling on the table. I really am. I'm pulling on the table, but it's not moving, is it? What's resisting that? Friction of the floor on the legs there. I am pulling on it, and it's not moving. Okay, finally I got it to move. That is static friction. The force that's resisting the motion of the table. That's static friction. Now, when I finally get it to move, okay, then that was kinetic friction. Okay, so I push, static, push, but then when it finally moves, I don't have to push as hard. Because generally, kinetic friction is less than static friction. Static friction, they're down in those grooves, and you have to do. Kinetic friction, they start riding on the tops, and there's not as much to overcome. Does that sort of make sense? So that's why when they're down in the grooves, that static friction, you have to exert more force to overcome that once it moves. You've probably seen that before. You pushed on something, but when it goes, you almost fall down because now you're moving into kinetic friction. And the kinetic friction is usually less than the static friction. All right, so that's one. Difference between static and kinetic. Okay? Now, the reason I said there's others, in some circumstances, people talk about rolling friction, which is even less than the other, but we're not going to talk about that, at least now. Okay? Now, here are three characteristics of friction. I probably need to go back to the other slide because there's not really a lot of room to write here. So here we go again. Oh, that worked pretty well. Oh, I hadn't written anything, that's why. Okay. So here, this one. Okay. Here's the first characteristic of friction. Whoa, let me get my pen back. Okay. 1. Friction is a force my writing stinks, so sorry about that, folks, that always, I've said this already, we've talked about it, always acts parallel to, now I'm not going to write the word, I'm going to put parallel bars there, parallel to the surface. I abbreviate like crazy, sorry about that. The surface in contact. Okay, remember our illustration before? The surface is down here, the normal is like, the surface like this, friction always is parallel to the surface of contact, okay? So, and opposite to the direction of motion. Now, we've said that already. Okay, remember from way back at the beginning, we said forces were vector quantities. They have direction as well as magnitude. So the direction is always opposing the motion. Motion is a vector quantity. Friction always opposes the motion. Okay? Number 2. Now, I just said this one. Static friction, I can't write. Okay? And I'm going to modify it slightly. Is greater than, occasionally, or equal to. Very seldom. The book doesn't put the equal to at all. There are a few objects whose static and kinetic frictions are the same. Most of them, time, static friction is greater than kinetic friction. Oops, I already put that in there. Kinetic friction. Okay? All right. And number 3. Friction increases as the force between the surfaces increase. Now that is, I don't like that sentence at all. Friction increases as the force between the surfaces increases. I can't write. Okay, something like that. Okay. Here's what they're meaning. Okay? Do you remember the forces between the surfaces? We talked about that on the slide earlier, the brick on the table. What do we call that? That's not what I want to do. That's not what I want to do. I want to do that. Okay. The normal force. Very good. Okay. That's your force between the surfaces, is your normal force. See, we go to 6:30. Okay. My last class went to 6, and I always have to remind myself. Okay? Now, if you have here, if these are 3 identical boxes, same weight, same roughness, same everything, this one on here, the effort force, of course, is going to have to be a certain amount. The friction force, this is static friction. If these are equal, that's static friction. But if you have 2 of those there, the static friction is even greater because the friction is proportional to the forces between the surfaces, which is your normal force. The more weight you have, the more normal force you have. That's what it's talking about. Now, so that's what the third one was. The more weight you have on it, then the more normal force you have pushing against it. Now, here's another example of that you may have hit before. If you're pulling on a wagon like this, or a sled, or something like that, pulling on it like that, you see your motion is this way, but your force has one component this way, one component up, because you're pulling this way. And because there's a component in this direction and up, you're actually decreasing the normal force on the sled because you've got a component upward. So actually that's easier. If you were, on the other hand, pushing down on somebody, like in a wagon, and pushing down and pushing from behind, but you don't want to get down there and push up, you're pushing like this, you're actually increasing the normal force because your push has a downward component. And you probably have seen and experienced that before too. Like pushing a wheelbarrow, pushing a lawnmower, pushing a cart. If you're pushing down on it, you're actually increasing the surface force, so you are increasing your friction force a little bit. Usually not too much, especially if they're rolling. Okay? So, that's way in the future. So let's go back to my other one. Okay. Here are a few other ones. Here is the formula for, and I wish I still had those up, but it deletes them when I go away from it. Here's the formula. The force due to friction, little f means friction, is equal to, it's the coefficient of friction, that's a mu, okay? It's a Greek lowercase m, which is a mu. The mu and times the normal force. That's the force between the surfaces, the normal force. Remember, it's perpendicular to the surface. So the friction force is equal to the coefficient of goodness, I can't think what they call that. The coefficient of friction. There's usually another name for it. The coefficient of friction. It's a ratio between the frictional force and the normal force. That's how you define it, so that's what it is. In the book, you have a table. Now, I'm not going to write all this table, and I wish it were on the slide set, but if you got your book, you can see it. You certainly aren't going to memorize these things. No, this doesn't do too bad. Okay, steel on steel has a coefficient of friction, that's your mu, of 0.58. That's static friction. Kinetic friction, 0.2. So that's less than half of it. So if you're dealing with static friction, this is F sub SF, then this would be mu sub S, static friction, coefficient due to static friction. If it's K, then that would be KF, then you mu sub K. So it's different mu whether you're static or kinetic. Okay? Steel on steel lubricated, static friction is 0.13, and kinetic friction says it's 0.13. So that place, it's the same. The coefficient is the same if it's lubricated. Glass on glass, 0.95 versus 0.4 kinetic. So you see less than half again. Hardwood on hardwood, 0.4 static, 0.25 kinetic. Not quite half. Steel on concrete, they don't even give a static. I don't know why, but the kinetic is 0.3. Aluminum on aluminum, 1.9, which is pretty large. And here's why. Aluminum is a soft metal. And if you have aluminum pushed across aluminum, because it's a soft metal, any of those microscopic grooves there are going to dig in. Not just go across, they actually dig in because aluminum is pretty soft. You don't need to know this, and don't get a big sweat about it. Rubber on dry concrete. There is friction you want to have. Static 2.0, kinetic 1.0. Okay? You want always that tire to be on static friction. You don't want the tire slipping over the concrete. You want the tire gripping the concrete. That's static friction. That's why, what's the name of that braking system? Anti-lock braking systems. As soon as it senses a sliding, it eases off trying to go back to getting static friction, because the static friction is greater than the kinetic friction. Because on kinetic friction, it's 1.0. It's exactly half. Rubber on wet concrete, though, drops to 1.5 static and 0.97. So it doesn't change much kinetic, but it does change big time your static. You want it on that. Aluminum on wet snow, 0.4. So that's pretty low. Aluminum on kinetic, that's static. Kinetic 0.02. I mean, that's 1/20th as much. You don't need to know these numbers. Steel on Teflon. Now, this is the one I was thinking of when I said some substances have very little change. Teflon is one. Static or kinetic is almost the same, 0.04, 0.04. Teflon is basically a lubricant. Okay. Now, the first time I ever heard of Teflon, that's what they coated pans with to make them non-stick. You couldn't get anything to stick on there unless you really burned it on good, or you scraped the Teflon and now you're down to the metal. And that's happened too. Okay. So, anyway, let's do example 1. And this isn't in the book, on the slide set, so let's do it here. I think I'll just leave that there because we're probably going to use it. Okay? A force of 170 newtons. Now, we don't know what kind of force that is, so we'll just say force is equal to 170 newtons. Okay? Now, question, how many significant digits? No. If you had a bar over the 0, that would be 3. Without the bar, it's only 2. Snuck that in on you, okay? Is needed to keep a 530 Newton wooden box. So this is a wooden box here. And the weight of that box, F sub W, is equal to 530 newtons. How many significant digits there? 2, absolutely. Sliding on the floor. So in other words, here's the floor. Sorry, that should be touching. Okay. Okay, it's touching the floor. Okay. And you need to have a force of, so this is the applied force of 170 newtons. Okay. It's necessary to keep that 530 Newton wooden box sliding on the wooden floor. What is the coefficient of kinetic friction? Because it's sliding, it's moving, so we're talking about kinetic friction. So remember what we said, the frictional force If this was required to keep it moving, that means that was what the frictional force was against it. So the ratio of the frictional force to the applied force, okay, and because this is the weight, that is also the normal force. F sub n is also 530 newtons because it's not going through the floor or flying off the floor. It's on the floor, so that has to be equal and opposite. Didn't we talk about Newton's third law, or did we? We only did the second law, so, but that's where that comes from, okay? So the push or the pull, whichever you're doing, the friction is resisting that. So this is also the force due to friction is also your 570. This is your normal force of the surface there. Remember the frictional force, here it is, there it is. The frictional force, which is 170 newtons, is equal to the mu sub k times the normal force, which was 530 newtons. Calculate the mu sub k. What would you do? Solve that equation. Solve for k. Divide by 530. Because you're trying to isolate the mu sub k, so you divide by 530 newtons. Fortunately, the units go out. Everything goes out here except mu sub k. You can divide by 10 there. 17 divided by 53. That's going to be a nice round number. What's that going to be? 17 divided by 53. Second, 0 point. What do you say? 32. What was the next digit? 0. So that's it exactly. Notice coefficient of friction, static or kinetic. This is kinetic. Has no units to it because it's a ratio of newtons to newtons. So that's 0.32. That's it. What is your mu sub k? Because that's kinetic. 0.32. Perfect. All right, and what I was just talking about before is friction and anti-lock brakes. That's exactly what we were talking about before. As soon as the car senses that you start sliding, it eases off, so it tries to go back to static friction and get away from kinetic friction. You can read that blurb if you got your book. The problem 5.4, any of the odd number exercise problems 1 through 15. Okay. They have an interesting little blurb there, new technologies on hydrophobic metals, how you go about reducing friction using those. Interesting. Okay. Now, yeah. Okay. Do anyone need to keep that one up a little longer? You got it, everybody? Okay. So let's, okay, go back to this one. All right. I thought we'd have the guys pushing on the thing, but we don't. Where is that slide? Oh, that's the next page. So I guess I need to go back to the one I was just at. Sorry. It takes such a pain in the neck to go back and forth like this. It's because they have such lousy PowerPoints. Okay. Get my pen back. All right. Total forces in one dimension. In other words, everything's moving in a straight line. We don't have any change of direction. Total forces in one dimension. When forces act in the same or opposite directions, that's still one dimension, the total or the net force can be found by either adding the forces if they're going the same direction or subtracting them if they're going in exactly opposite directions. Okay? Often useful to draw the forces as vectors, and that's exactly what we're doing. So, rather than drawing it, let me show you the picture. You can draw it if you want to. Okay, here's what you got. You got two guys pushing on this big old container here. Now the big guy over here is pushing with 175 pounds of force. The little guy over here is only pushing with 150 pounds of force. That's all he can muster. So what is the net force pushing on the box? So the little guy had a net force, and what we usually do is what we call a free body diagram. We count the box as just a point, and the big guy is pushing with 175 or 70? 175 pounds, and the little guy is pushing with 150 pounds. Okay, I can't write. Okay. Okay. And I drew these as vectors, 150 pounds. What's the net force being pushed on the box? In the same direction, so the net force here, that's not normal force. Let's do little n for net force, is equal to 225 pounds. Okay? Now, 325, I can't add either. Okay? I was thinking 3 and for some reason wrote 2, said 2. Let me clean that up a little bit. Okay, that's net force, and clean that up and make it a 3. Okay, 325 pounds. Okay, now, we're not multiplying, we're adding here. So that is 3 digits, and even though there's 0 is not significant, you're adding those things so you can count that as if that were. So the rules are different for adding and subtracting. So we'll leave that as 325. All right. Now, the same 2 workers push the crate to the right, and the motion is opposed by a static. Now, originally, we were saying, let's see, 2 workers push in the same direction, the force exerted by one, okay, blah, blah, blah. Oh. They didn't write it on the picture, but they wrote it in the text. 150 pounds. So that was exactly 3 digits. So that's why we were able to get away with that. The force exerted by the other is 175. Net force exerted, find the net force exerted, that's what we did. We just add them up. Okay. Now the book introduces this. Anyone know what that is? That is the Greek letter, capital letter sigma. And it means sum. Add it up. That's all it means. And they threw this in for some reason. So we say the sum of the forces is add that force to that force. So that's all we did. You don't need to know that. Okay. So that's how much they're exerting. Now what we don't know is that they moved it at all. They may have just been pushing, and if the static friction was more than 325 or equal to 325, they aren't moving it. Okay? But let's say that they are moving it, but that no, they're not. 2 static push the crate to the right, and the motion is opposed by a static frictional force of 300 pounds. Okay? So the maximum static friction, and I'm going to put ST for static friction, is 300 pounds. Okay? Both of those zeros are significant. What is the net force on the crate? They're pushing, and this is no longer net. This is the applied force of 325 pounds. The static friction force is 300 pounds. So what's the net force now? That's equal to 25 pounds. Now, when you're subtracting,
You said it not moving?
No. If that were the case, now there's a problem with this problem, and that's why I was trying to finesse my way around with this example. It wouldn't be static anymore; it would move to kinetic. But they didn't give us the kinetic friction force, so I had to use a static. You would have a net force in the positive direction of 25 pounds. Now, notice when you're subtracting, you don't do significant digits like you do multiplication and division. If you had to the nearest pound, which we did, the nearest pound that we did, your answer is to the nearest pound. You don't introduce another 0.0. If you're multiplying or dividing, yeah, you have significant digits. When you're adding or subtracting, you do to the nearest last digit. And that's all you can do. Okay? So that would be pound. The net force would be 25 pounds to the right. It would, you have exceeded the static friction, so you moved into the kinetic, but they didn't tell us what the kinetic friction was, so that's all we can do. Net force to get it moving would be 25 pounds to the right. Okay? Now, that crate in example 2 has a mass. This represents the crate. So let me draw it as a crate now. Okay? The mass of this crate, and this is a made-up problem, is 5.00 slugs. Okay? 5.00 slugs. What is the acceleration when the workers are pushing against the frictional force? Well, the net force on it is 25 pounds. The mass is 5 slugs. So what would be the acceleration? What formula would you use? Yes, the net force is, and that should be little n. Because they've already introduced capital N as normal, we should be calling that little n for net force. This book doesn't specify net force, but it really is a good idea to do so. The net force is equal to the mass times the acceleration. Okay? We know the net force is 25 pounds. We know the mass is 5.00 slugs. We're looking for acceleration. That's the unknown. How do we get it? Divide by 5. Divide by 5.00 slugs. And in that case, I don't want to write that as pounds. I want to write that as the fundamental units, which are slug feet per second squared. Remember, that's what a pound is, a slug foot per second squared. So when you divide both sides by 5.00 slugs, units are your friends. Be kind to them. The slugs cancel out, and you're left with what? 5.0. 2 significant digits there, 3 there. You have to go with the lesser. 5 feet per second squared. That would be your acceleration. And that's what they got in the book too. 5 feet per second squared. All right. I think we got time for example 4. Y'all okay with it? Okay, let's go to example 4. Let me erase this one. All right. 2 workers push in the same direction on a large pallet, a lot like before. The force exerted by one worker is 645 newtons. Okay, so one is 645 newtons. We'll call that F1, worker 1. The bigger worker, F2, or the stronger worker or whatever, is pushing with 755 newtons. Okay? The motion is opposed by a frictional force, so the oppositional force, F sub F, is going to be 1175 newtons. Okay? The motion, okay, right. What is the net force on that pallet? So the net force is, I'm going to call it little n, is the sum of these 3 forces. Okay? And that is 645 newtons in the positive direction plus 755 newtons in the same direction, positive direction, but being opposed exactly by that, so that'd be a minus 1175 newtons in this. What's the net force then? Add, then subtract. What do you come up with? Say again? A little louder.
225.
55?
225.
Two what?
225.
My hearing's bad. Okay, 225. 225 newtons. In the positive direction, you overcame that because this adds to something, what is that, 1390 minus, ooh, that's not right. Yeah, no, 1400. 1400 minus 11, I could have done that in my head. Minus 1175 is 225. You're absolutely right. Okay? Good deal. They didn't ask for an acceleration, so we didn't do it. They didn't give us a mass, so we didn't do it. All right, problems 5.5. Do any of the odd number problems 1 through 13. You choose which ones, how many, and whatever. Ha! Now I see why we hadn't done Newton's third law. They're just now getting to it. Okay? So let's go back to, y'all got this one already? Okay? So let's go back to the slides. And here is the one we're coming up on. All right, from current slide. All right. This is Newton's third law. Little bit of review here. Newton's first law, the law of inertia. If an object is at rest, it stays at rest unless acted on by an unbalanced force, a net force. If it's in motion, straight line motion, it continues that motion, doesn't change its inertia unless it's acted on by an unbalanced force. Now, the unbalanced force may be friction. Rolling across the table, it's got some friction. You can hear it roll, can't you? If it's sliding there, you wouldn't hear a thing, you know. Okay, maybe. Okay. So that's Newton's first law. Second law, if there is a net force, it's going to accelerate. It's going to change its velocity. That's Newton's second law. F equal ma. Force, net force is producing an acceleration. Acceleration meant there had to be a net force. So here's Newton's third law. Okay? And here's how they're going to introduce it. Okay? When an automobile accelerates, we know that a force is being applied to it. You have to have a net force for it to accelerate. F equal ma. It has to be a net force. What applies that force? Well, when you get right down to it, the tire is pushing on the road because the engine's turning the wheel's turning this way, it's pushing against the road that way, and if there's a friction this way, and it's pushing that way, you have a net force of 400 pounds in that direction, so you move that way. So really, what causes that is the friction of the tire on the road. And you want that to be static friction. You don't want it to be sliding, kinetic. Because if that's sliding, you don't have as much control, you lose, because you want the that to be a static friction case. Okay? Now, I would not have introduced the law of action and reaction this way, but that's how they do it. The third law of motion is the law of action and reaction, and I'm sure they don't have it stated here. There was active shooter in that one. Okay, so I'm going to try to write it on here because it's just one. Okay, now let's go back to the first and second law. The first law, you're talking about an object. It's either at rest or it's in motion. The force is acting on it or not acting on it, acting on that object. Net force acting on an object. Second law, okay, is on that object. Newton's third law always deals with two forces. Okay? Now, and supposedly, Newton expressed it this way. If I push on a rock, the rock pushes on me. Look at that. You'll have to dip my finger. That's not a rock, it's a table, but you get the general idea. That's action-reaction. I'm pushing on the table's pushing on my finger. Action-reaction. They're always equal and opposite. Always equal and opposite. Okay? That's why I didn't like this example to introduce it. Okay? So, for every force applied by object A on object B, see we got two objects now, that's the action, there is an equal and opposite force exerted on B by A, and that's the reaction force. Okay? Now, here is sort of a classic example of that. Are any of you fishermen? None of you like to fish. Oh, you have. Okay, all right. Do you ever go out and say a bass boat, a lightweight aluminum bass boat, and fish? On the shore. Okay. You've probably seen, at least in cartoons, but you've seen somewhere people getting on and off of boats, right? Especially those lightweight aluminum bass boats or something like that. Okay? Let's say that your buddy that you're fishing with forgot to tie up the boat, and you weren't alert enough to notice that. Okay? You thought he had. So here you're on the boat, going to step onto the dock. So guess what? Stepping on, you're pushing against the boat. Okay? You push against the boat, and if he had tied it up, the boat pushes on you, you step onto the dock. But if you forgot to tie it up, you push on the boat, and the boat takes off and goes, and you splash into the water. It happens in cartoons all the time, right? Okay. So you have watched cartoons, right? Okay. That's action and reaction. You push on one thing, it pushes on you. If it was tied up, you push on it, it pushes on you, you step aside. If it's not tied up, you push on it, it doesn't really push much on you, so it takes off, and you go right down. Okay. So, action, reaction. Okay? That's Newton's third law. And we didn't get very far at all on this one. We will pick up there next time. Okay? And unfortunately, it's going to be the active shooter example, not active shooter. It's going to be firing a weapon. And we will talk about that. This section has no problems in it. And we are right at the end of the chapter. Okay? And I didn't think we were going to get this far today, so I don't have your first test ready, but I can go into the office there and make it. I do have it ready, I just don't have copies made. Would you like to take it home so you can start working on it? Yay or nay? Okay, good. Let me find it for you, and I'll do it. We're not quite finished, but we're close enough. I would hate for you not to have that. Okay? Here we go. Does anyone need to leave right away? I've got one copy made. I need to make that. You need to leave right away. Okay. Let's see how many. Check and make sure there's nothing on the back of that. Okay, good. That's fine. Let's see how many I need. Yeah, here we are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I need 15 copies. I'll be right back. Let's set up the copy machine on.
Chase study is like 14 something. And if you don't already have it, you can send it out and someone will get back to you.
They did leave it on. It was in standby mode, but it came up pretty quick. Now, I think this test is correct as written, but remember, you always have one class you can ask me questions on, So next class, get started on this. You have a whole week. So next class, ask me questions. If you have anything you don't understand what they're looking for, I believe they're very similar to the ones in the text. So look at those problems, make sure you understand how to get those, and you should be able to go from there. I know that last problem, number 10, we'll have to go over the stuff. That's where we left off today. No, that's the wrong test. I'm sorry, I gave the other student the wrong test. Where is the... Where is my... That... Give me those back. Where's my test? Okay, that's chapter 8. Okay, sorry about that, folks. Y'all don't need to do this one. And that gal who was here, y'all know her? Okay, I hope you listened to the thing. That was the wrong test. Don't do it yet. But at least I have this one made out already. Let me see. There is, that's it. There it is. How did I do that? Okay, I have 2 of these available. I need to make 14 copies. Okay, anyone need to go right away? Who wants to get out first? Okay, there's one. Okay, well, I got an extra one. Okay. So I'll make 14 copies of this one.
Work some everywhere. For the, I actually work for I know everybody. After he created the program, the supervisor that's over, they're going to take with and approve all of them.
Bad news, they just ran out of toner, but I have enough for y'all. I have enough for everybody else, but I have enough for y'all. Quick copy. All right. Did you get what you did? Okay. That's the right one. Now I have to make more copies next time. Okay, this one you can do all of. Okay. You can do all of those. If I hadn't looked at that one, I would have. Okay. Sorry about the confusion. I'll have to straighten all that out later. Good deal, folks. Sorry we ran over a little bit. Okay, what do y'all think about the pace of the class? Too fast, too slow, or is it okay? Yeah. Y'all can agree or disagree.
It's also a little fast, but I'm just going to review. So,
Okay.
Hopefully
All right. Well, if you ever want to maybe slow down, hey, okay. He's up a bit here. I'm fine with it. Okay, good deal, folks. Ooh, my knee hurts.
So that first video is already on.
Okay, I don't have the link there yet. I'll try.